Thank you all for your interest in this webinar. So just for a little bit of context, this is a webinar that we originally gave in person 2 weeks ago during New York Climate Week. And, people seem to find it interesting. And so we decided to offer up the same webinar, more or less the same content in a webinar format online. And so that's what we'll be hearing today. So just some logistics and a quick outline here. What I'm going to be talking about today is really giving a high-level overview of the weather and climate data ecosystem from my point of view as a practitioner and developer in this space for many years. We'll talk about what weather and climate data are useful for, where do they come from, and then talk a little bit about the technology for working with weather and climate data, including the platform that we are building here at Earthmover. This is going to be a lot of fun. We're really looking forward to a conversation at the end, so I'll try to finish up with some time left to do some questions and discussions and all of that good stuff. Let's keep this informal. We are recording, so perhaps let's leave the questions till the end, but certainly going to have plenty of time for discussion. Any questions from people, points of order before we get started with the webinar? Yes, go ahead.
Hi, Ryan. Just to know, can the recording will be somewhere in the website to get it for the latter reference?
Absolutely, yes. We will certainly be recording this. It's recording now, and we will be sharing the video as well as the slides.
Appreciate it.
All right. Yeah, Ali, go ahead.
Yes, hi. Just wondered, the webinar is like New Year, NYC Climate Week. We have every week, or I know for LEAP project we have a weekly webinar. So how was for NYC Climate Week?
Climate Week is just a once a year event. So Climate Week was something that took place here in New York 2 weeks ago. And so it happens every year. I'm gonna get started now.
Okay, that's nice. I wanted to have like it's for 2 weeks and we can participate online. How is that for Climate Week for next year? I mean,
Climate Week is a large distributed event in New York City that is probably too complicated to try to describe in its entirety right now, but just look it up, Google it, you'll find plenty of information about Climate Week online. Okay, so let's dive into it. I see people are still joining. I guess I'll start by just giving an introduction to myself. Who are you listening to today? So my name is Ryan Abernathy, and I'm the CEO and co-founder of Earthmover. Through my career, I've moved through a couple different hats, so to speak. So really my background is as a scientist. I'm trained as an oceanographer and climate modeler, and that's the field I've been working in for almost 2 decades at this point. Until recently, I was a professor at Columbia. I got very involved in the open source and open data community, and we helped start the Pangeo project in 2017. And through that work, I got super involved as a developer on projects like X-Array, ZAR, and a lot of the technology that's used in this space. And then most recently, about 2 years ago, we started Earthmover. We're a tech startup. Our mission is to empower people to use scientific data to solve humanity's greatest challenges. In fact, that's my next slide. So a bit about our company. Earthmover, yeah, we're a small startup. We're bringing together folks like myself with a background in scientific data analysis and research, with a bunch of really great engineers who have built production-grade systems at some of the top tech companies in the world. And we're really aiming to take the whole practice of cloud-based scientific data management to the next level. So I'll tell you a little bit more about our platform towards the end of the talk when we're talking about the sort of technology aspects. But for now, I'll leave it there. To get started, I want to look at what I mean by weather and climate data. So this is one of my favorite animations. It was developed by the NASA Scientific Visualization Studio, and it shows many different Earth system fields all together on one globe. And to me, this video just drives home what an amazing time it is to be working with weather and climate data. We have more data about the Earth system than we ever did before. It's coming in from satellites, from simulations, from sensors. And so in many ways, we're living in a golden age of data. We have access to data that past generations of environmental scientists could have never dreamed of. On the other hand, this data is a big challenge to work with. It's very large, it's very complex, and so this is really the core focus of our webinar and of my work overall, is to make working with this type of data easier to do for scientists, data engineers, and other practitioners. So, what do we mean when we say weather and climate data? Well, I want to make it clear that we're really talking about a complex physical, chemical, and biological system that together we call the Earth system, right? So the Earth system is really, the full system of all these different components that interact together, and each of them affects the other, right? So maybe we're interested in the atmosphere, but of course the atmosphere is deeply influenced by the ocean. Maybe we're interested in the land, but of course the land depends on the atmosphere. And so, my viewpoint is that we really need to take a holistic view to the Earth system and model and understand and study these components together. And in fact, this is how the modern field of Earth system science works. So when we're thinking about weather and climate data, we're really thinking about all of these different components of the interacting Earth system. However, today we'll focus mostly on the atmosphere, the hydrosphere, and to some degree the cryosphere when we're thinking about weather and climate timescales, and not going to delve so much into biology today. So before getting deeper into the sources of data and how we work with the data, I think it's useful to zoom out and start with this question of what are weather and climate data used for? So here's a perspective I developed that I think is very important for folks who are coming into this field to think about. The Earth system is constantly changing, and there are phenomena that are unfolding over many different time scales and spatial scales. And so for a particular process of interest, it's useful to locate that process within this two-dimensional space of spatial scales and temporal scales. So to give an example of what I mean, a very familiar phenomenon that's clearly quite relevant to a lot of different impacts are tornadoes. Right? Tornadoes do a lot of damage. They're very high-profile weather events. Tornadoes are pretty small scale in both space and time. So tornadoes, exist on the scale of kilometers, and they evolve over minutes to hours. They're not lasting for days or weeks. And most of the sort of weather and climate phenomena that we're interested in, that we think of as impacting, our society and our well-being, can be located similarly within this space. So severe storms, they can be larger than tornadoes. They're still not lasting, much more than days. Hurricanes, of course, very much on our mind right now as we have the aftermath of Helene, and then the new hurricane that is about to hit Florida. This is, obviously a huge focus for folks who are thinking about climate risk and weather impacts. Hurricanes are much larger scale phenomenon, up to 1,000-kilometer area can be affected by hurricanes, and they last for many days to weeks. Going out farther, we start to encounter some other types of processes and timescales. And one climate phenomenon I think that's useful to think about and recognize are the seasons, right? So seasons are a really fundamental feature of our climate system, right? And of course, seasons have a very fixed temporal scale, and they affect the entire planet. There are other modes of climate variability that occur on even longer timescales than seasons. So you might be familiar with phenomena such as the El Nino Southern Oscillation. These oscillations in the climate system affect very large scales, and they play out over long timescales. Just about every process we might be interested in terms of climate impacts can be located somewhere in this space. So here I've drawn circles for flood and wildfire, marine heat waves, and drought. And of course, at the longest time scale, we have the phenomenon of climate change itself, which is playing out over decades and centuries. That's really the time scale at which we can observe those direct climate changes. But one challenge around climate change is that it itself is affecting the statistics of all these other more short-term processes, right? So while tornadoes themselves are very short-lived, there is evidence that the environmental conditions that underlie tornadoes are changing with climate change. And so this very large scale and slow evolution of the climate system does feedback and interact with these much smaller scale processes in space and time. Now, why is this important? Because different data sets have inherently different spatial and temporal resolution. And so depending on what you're interested in, different data sets, different sources of data may be more or less appropriate for studying and understanding one of these phenomena. Now, one thing that I think is very interesting to do is to overlay these spatial timescales with the timescales and spatial scales of typical business interests, right? So here's an example of me attempting to do that with the financial sector, right? So different businesses, different verticals think about problems on different timescales as well, right? So you're probably familiar with the world of high frequency traders. These are folks who are exchanging assets over sometimes milliseconds, seconds, minutes, maybe hours. And they're interested in only very short-term fluctuations in the market, right? As we move to longer timescales, we encounter more of this sort of traditional equities and asset management side of the economy. And then finally, as we move out to the longest timescales, we encounter sort of the long-term asset managers, the mutual funds, et cetera, who are managing money on timescales of decades. Right? So this is just a rough attempt to match up those different business timescales with the physical timescales of the climate system. And it's quite interesting to me to think about who cares about what within this landscape. So this makes it clear that most of these types of financial institutions or players are really not incentivized to think about long-term climate change in their day-to-day operations, because it just doesn't overlap very much with those timescales, except as we go out to maybe the largest timescales. However, we do know that climate change is feeding back on those shorter timescales and affecting those processes. And so, there's a very interesting interplay here. And this is something I am interested in exploring a lot more. So, this is attempting to explain, why, different fields of industry may be interested in weather and climate data to the extent that it overlaps with their business timescales. Now, whose bottom line is actually impacted by weather and climate phenomena? Well, it's it's really easy to go through a list of industries and see that so many different parts of our economy are waking up to the fact that they are directly impacted by what's happening within the Earth system. Agriculture is, of course, one of the most common examples of this. Forestry. Energy is, of course, a huge example of an industry, both on the demand side and the supply side, particularly when it comes to renewables. And so just, go down the list. What we're seeing from our point of view is a rapidly growing interest among many different industries in leveraging weather and climate data in order to improve business outcomes. And so that's been a big part of our focus at Earthmover, is helping these type of folks to engage with and work effectively with weather and climate data. So one way we like to think about how folks can do that is through the data value chain. Right? This is another framework we've developed that really helps us think about how different types of organizations are interacting with weather and climate data. And of course, this is a simplification, and but it's turned into a useful framework for us to think about this landscape, right? So weather and climate data ultimately are originating with data providers, folks who are generating raw data sets, either using simulations or direct observations. And many of those are on the public sector. We think of course, the big satellite data providers like NASA. But there's a growing number of private sector data providers as well, mostly folks operating satellites. At the far other end of the spectrum, we have the data end users. And so I'm just listing a few examples here. These are companies or institutions with actual assets that are at risk to environmental factors, whether on the weather or climate timescales. And so, a well-known example is the hedge fund Citadel. They're on the record as having a very established weather modeling program in-house that allows them to trade commodities more effectively around weather data. Of course, we've got insurers who are very interested in this, the entire energy sector, and of course, governments around the world, are thinking deeply about this. These are just a few examples of folks, who actually care about the sort of direct impact on their own assets from weather and climate. And then in the middle here, we've got a whole range of very interesting companies and organizations that we would call data refiners. And what data refiners are doing they're generally consuming raw data, this more basic sort of data from data providers, and refining it, adding value to it using various types of modeling, statistics, or AI and ML, right? And so I've just listed a couple different companies. Some of these are very small startups. Some of these are big, multinational companies and consultancies. And what data refiners do are they're taking raw information and translating it into something that's more useful, more actionable for the end users. Of course, there's also an arrow going directly from data providers to the data end users, and that's an arrow I'm interested in as well. There's, I think, a lot of opportunity to make raw data more useful and more accessible to everyone, not just specialized agencies. And so we'll touch on that topic a bit later in the presentation. Okay, so that's an overview of what weather and climate data are used for, broadly speaking. A quick one, but hopefully touching on the main points. I'd like to spend a lot of the rest of the time discussing where weather and climate data come from. It's very important to acknowledge that weather and climate data occur in sort of a couple different locations in time. There's what happened in the past, what's the history of what's happened on our planet. There's the question of what's happening right now. And then there's the question of what's going to happen in the future. And in many cases, the question of what's going to happen in the future is a very valuable one, because having some information about the future allows you to make plans and take a financial position regarding that future. However, it there are literally no data about the future. So understanding what's going to happen in the future is fundamentally a modeling problem. And so we're going to see that models and simulations become quite important quite quickly in the discussion of weather and climate data. But let's start first with the concept of raw observations. So when we're thinking about, just basic weather data, where does that, information originate from? How do we know what the weather is on the planet? Well, ultimately, the most reliable and valuable source of observations about our weather are what we call in situ data, direct observations from weather stations that measure temperature, wind speed, radiation, other properties directly from the air. We have weather stations all over the world, and we increasingly have a network of radiosondes or balloons that are launched and can get us the same type of data from throughout the atmosphere, not just on the Earth's surface. And so here is a little visualization of these radiosonde launching sites, the sort of standard locations where these balloons are launched from on a sort of daily basis. This information is collected and it's fed into our weather systems and provides sort of the backbone of a lot of what we know directly about the atmosphere. However, as you can see, this is still a pretty sparse network. It's not as if we have weather stations, on every block or balloons being launched from every house in the world. So that's where, in order to, get a more comprehensive global picture, we bring in the concept of remote sensing, right? So remote sensing or Earth observation is, in general, the process of using satellites or aircraft as well, but mostly here focusing on satellites to observe what's going on the Earth. And so today we have a massive fleet, international cooperation around launching weather satellites, which observe our atmosphere and land, the ocean, and gather that information and relay it back down to Earth. Here's a nice movie of this from NASA showing NASA's Earth observation fleet. NASA does great movies, so I like to use those. This, I think, just hopefully gives across the idea that we really have a lot of satellites up there. They're observing a lot of different properties. And I think if you're new to this area of weather observations, weather and climate data, if you think about satellites, you probably mostly think about satellite imagery, something like we see on the left. So on the left is a Landsat image of a wildfire. But I think when thinking about this weather data, it's important to understand that a lot of our remote sensing is doing very advanced, complex sensing of different physical variables far beyond just visible imagery, right? So to call this type of satellite data, imagery would be a pretty incomplete description. Often we're using very active instruments like microwaves, or we're doing really fancy things like synthetic aperture radar. What I'm showing over here on the right is an example of the NASA Surface Water and Ocean Topography satellite, a satellite that uses radar interferometry to measure the height of the ocean surface and turn that into an altitude. And so, the point here is just to convey these satellites are really quite complex, measuring a lot of different physical quantities, not just taking pictures. Okay, so that's great. We've got all these weather stations. We've got all these complex, fancy satellites. What if you just want to know the weather at a particular place on Earth at a particular time? Right? What if you don't want to process, all of these satellite observations yourself? Well, this is where models start to come into the picture. And so now I'm going to spend some time talking about how we use models or simulations in order to help synthesize and draw together all of these observations into a coherent picture of what the Earth system is doing. So let's talk a little bit about Earth system models. So Earth system models are really a way of turning our physical understanding of how the ocean and the atmosphere and the land system work on a first principles basis into a program that we can run in a computer. So this process works starting from an equation that we know and understand and have a lot of confidence in, something like the Navier-Stokes equation that's shown here, which describes the motion of fluids, such as the atmosphere or the ocean. We then take the Earth system, either the whole Earth or some smaller region of it, and split that up into what we would call a grid. So we discretize it, turn it into pixels, and then we write a bunch of computer code to effectively simulate what happens when you let those equations evolve over time. These are very sort of long-standing, established programs for scientific computing. Most of them are written in Fortran, old school programming language. They're very powerful and they're very complicated. So these Earth system models, for the most part, are run on pretty big supercomputers, certainly if you're doing work at a global scale. And the computational cost of running these Earth system models is very directly tied to their resolution, right? And so in that early slide, we talked about the different sort of spatial scales of different phenomena. And here we can see that as we, in order to model the Earth system, we need to represent it as a sort of grid of pixels. And the number of pixels we use determines how fine that grid is. So we're able to represent more and more complex fine scale phenomena as we move to finer grids. But that comes at a cost of increased data volume and increased computational costs for those models. So, our largest, most state-of-the-art Earth system models run on massive exascale supercomputers, such as this one, Frontier, a DOE supercomputer that is shown in this image. Right? So this is a very computationally intensive undertaking. Here's an example of the outputs of one of those models. I'm an oceanographer, so here I'm showing some data from a NOAA GFDL ocean atmosphere coupled simulation. It's showing ocean currents and ocean temperatures. This was made by Julius Puseke. What we can see a huge amount of fine resolution detail in this simulation. This was run on a big supercomputer, produced a massive amount of output data, and it looks very realistic, looks very natural. So this is an example of one of these Earth system models. Now, what I've just showed and what I've just described is essentially a free running model. It doesn't say anything about data. We started this conversation on what are the sources of data that we can use, to understand what's happened in the past, present, and future on the Earth system. And so at some point, we need to bring in that data. How does that work? So what I'm going to describe on this slide is a very, very simple, but I think accurate overview of this process of bringing models and data together through the process of data assimilation. Okay, and so what I've got here is just a very simple thought experiment. Say we are observing a ball moving through the air, and we observe it at two different positions and at two different times. So we can see at time 1, the ball was here. At time 2, the ball was there. Our sort of most naive prediction about where this ball might go would involve just drawing a straight line between those 2 points. And if you didn't know anything about physics, that would be a fine way to predict how that ball is going to evolve. However, we do know something about physics. We know Newton's second law, F equals ma, right? And we know that this ball is on Earth where there's a gravitational field. And so we can actually make a model that predicts how the ball might move through space. And it's not as a straight line, but it's actually following a parabola. And so if we are going to, fit that data to a parabola, we'll make a very different prediction than if we were just making a naive prediction based on a straight line, right? And we would predict that instead of going up, the ball is going to come down. Now, this is a really simple example, but it goes to show that by bringing physical understanding in the form of some type of model, together with observations, we can create a much more accurate representation, and not only a prediction of the future, but also ability to interpolate through the past where that ball may have been in the past. So this is essentially how our modern weather and climate data systems work today. We take all of the available observations from satellites and weather stations, and we feed them through a data assimilating physics simulation. And we run this on a big supercomputer, and this spits out a synthesized view of what happened and what will happen. And we describe this as an analysis, a forecast, and a reanalysis. And this process is constantly running. It's operationalized by our national weather centers and meteorological bureaus around the world. And so let me say a little bit more about how this works. But first, here's an example of one such data assimilations, right? So here is some data assimilation from NASA GMAO, and it's showing precipitable water. And we can see, this is a computer simulation, but it looks just like the real world. It's providing this consistent global sort of gap-free view of what the weather did. And this is really, really useful for all types of analysis and forecasting and research. So how do we get something like this? What is the process involved? Well, essentially, we're continuously consuming observations and synthesizing them into a best estimate of the current state of the atmosphere. That's what we call analysis. From that analysis, we then run a forecast, which is stepping forward this sort of numerical model using those equations, and then creating an update with the latest observations as they come in. And so this is the operational cycle used, for example, at ECMWF, the European Center. They are generating multiple different timescales of forecasts. So some of them are just going a short distance out. Some of them are going much longer, days and weeks out into the future. And so this is constantly producing and generating data that we can then use in order to both study the past, the current state, and the future of what the weather and climate system is going to do. And I think it's a remarkable scientific achievement that these weather forecasts are getting better and better all the time. And so what you see here is a sort of plot showing, since going back to the beginning of the 80s until about 2018, the skill score for various ECMWF forecasts. So, the skill score, of 100 would essentially mean a perfect forecast, and 0 would mean there's really no skill. And these are different time horizons, so 3-day forecast, 5-day forecast, 7-day forecast, 10-day forecast. And what we can see is that there's been a steady increase over time of the skill of these weather forecasts at all time scales. And that means, two things. A, we're getting better data to feed into these models, and 2, we're getting better modeling capabilities that are allowing us to synthesize that data and make better predictions. And so this is a remarkable achievement of science and engineering, and it's something that these data are free and available for everyone to use and leverage for all kinds of purposes. So it's a wonderful sort of public good that exists in the world. Here's a pretty short rundown of just what seem to be some of the most popular weather forecast data products that are available that we see folks using, particularly in the US. Certainly the European Center for Medium Range Weather Forecasting, ECMWF, produces some very popular weather forecast products. They're HRES, high resolution 10-day forecasts. They're ensemble 15-day forecasts, and they also produce a seasonal forecast that is of interest. On the US side, it's the NOAA, National Oceanographic and Atmospheric Administration, that's producing weather forecasts through the National Weather Service. They are producing the GFS, the Global Forecast System, the GEFS, Global Ensemble Forecast System, which is probabilistic, and then the High Resolution Rapid Refresh Forecast, which is focused on the US. There's many other forecast products out there, but these are some of the most popular weather forecast data products that we see folks using. It's also a really exciting time to be in this field because there is a huge crop of new AI-based weather forecasts that are being produced both by big companies like Google and NVIDIA or smaller startups like Jua, Zeus, Xcarta, Salient, Silurian. These are all folks who are using advances in AI to come up with new ways to do weather forecasting and are producing data that in many cases are competitive with, or in some cases better than what you can get from those traditional simulation-based or HPC-based weather forecast products. And so this is a really exciting place to be, and we're going to be keeping an eye on this space quite closely. Switching gears a little bit from forecast to this question of, what has happened historically. There's a very important category of weather and climate data product called reanalysis. And so reanalysis is, instead of trying to answer this question of what happened in the future, reanalysis focuses on what happened in the past and how can we reconstruct the history of what's happened in the atmosphere and ocean over the past decades. So reanalysis uses the same basic framework as weather forecasting, except it goes retroactively through all of those observations using a careful quality control process to produce a physically consistent, gap-free, jump-free record of what happened over the historical period on a harmonized spatial and temporal grid. And so reanalysis is the type of data that's useful for long-term historical studies of climate. So reanalysis is, for example, is how we know how much the Earth has warmed over the past few decades, which is a really important piece of data for say global warming studies, right? And so here you can see another nice figure from ECMWF showing what those global air temperature trends are over time. So reanalysis, there's a lot of great reanalysis products out there. ECMWF ERA 5, NASA's MERA 2, NOAA has quite a few different reanalyses. There's specialized reanalyses focused on just the ocean. This is a very active topic of research, so there's many relevant data products out there. But if you're looking for a sort of view of the history of what happened on Earth historically, then reanalysis is a really good place to start. Going a little bit beyond the weather timescales of about 2 weeks, we enter into the world of climate forecasts. So climate forecasts sort of start at this subseasonal time scale, 2 to 12 weeks, and go out beyond there. And as we move into the climate forecasting timescales, the predictability that we're getting is coming from other sources of information than just what are the initial conditions of the atmosphere at the initialization time, right? And so this has to do with sort of the large scale state of the atmosphere, including the ocean and the stratosphere, as well as the forcing and feedbacks that exist in the climate system. And so this is a pretty active topic of research, but we are starting to see a growing number of seasonal and subseasonal forecasts come online that are leveraging various sources of predictability within the Earth system to provide that longer term outlook. These tend to be much more probabilistic in nature, but these are interesting, particularly on the business side, folks who want to have some data to make some decisions on a bit longer timescales than what's available with weather forecasting. Finally, as we move into the longest timescales, we move towards the area of climate projection. And climate projection is essentially using the same type of models or simulations that are used for weather forecasting, but running them out to much longer timescales. And so climate projections really grow in terms of their uncertainty as we move out to longer timescales, but are necessary for us to do in order to understand how this planet is going to evolve in the future, right? And so you can see these nice figures from the IPCC report sort of show the main sources of uncertainty in projected global mean temperature as we move out. Right? And so there's really three main sources of uncertainty in these types of forecasts. One is just the internal variability of the climate system itself, inherent unpredictability of the climate system. That's shown in orange. The blue is what we call structural uncertainty, and it's related to our confidence in our ability to accurately model the Earth system, right? And so structural uncertainty really tends to dominate our uncertainty in our climate forecasts going out over the next several decades, which is why it's so important to be improving these models, improving how they work, augmenting them with AI, et cetera. On the longest time scale, though, all of the uncertainty really comes from the emission scenario. How much fossil fuel are we going to burn, and how much greenhouse gases are we going to emit into the atmosphere? And that's, that's up to us to answer that question. We can't, no model is going to be able to predict that for us. But this is just showing how that really is the main determinant of our long-term fate here. I'd like to spend some time talking about, climate modeling and, in more depth and this climate projection data. And so here I'm going to be using some slides that were sort of adapting some slides that were created by Julius Buseke, who gave this talk with me when we gave it at Climate Week. I think we're all aware of the really strong impact that climate change is going to have on our planet, on our everyday lives, and on our economy. Every year we're getting new examples of climate-related phenomena that are impacting our lives. And so understanding how to get the best data around what's going to be happening on the future of for the future of this planet is a really important priority for lots of folks. And so it's important to emphasize that, the way we know, the main way we know on a quantitative level, what's going to happen to the planet in the future is through this climate modeling enterprise, right? We take these Earth system models and we run them forward under a bunch of different scenarios, and those eventually produce graphs like this one that show how temperatures may evolve under different emissions scenarios, right? So these different SPFs represent different amounts of greenhouse forcing that may be emitted into the atmosphere. So I want to spend a little bit of time talking about, where these data come from and how this process of climate modeling actually works. So the main source for all of our climate projection data comes from the Coupled Model Intercomparison Project, or CMIP. So this is an international effort coordinated by the World Climate Research Program that aims to align and coordinate all of the different climate modeling centers around the world towards a shared goal. And what CMIP does is define these emission scenarios and experimental protocols for each of these modeling centers to run. And then each of these modeling centers goes back and comes up with the best climate model they can using the state-of-the-art, science and computer science and technology. And they run these projections, and then they submit their data to CMIP. And CMIP also helps define sort of the data standardization process that is going to accompany that data. This began in 1995. We're on our 6th version today, and CMIP 7 is starting to spin up. And it's a really, wonderful and incredibly impactful area of global international scientific collaboration. It's so useful to the scientific research community to have these protocols and to have the data sort of standardized in a way that makes it easy to use. There's dozens of centers around the world at this point that are contributing to CMIP and that are working together on this sort of experiment. And so I think this is phenomenal. In terms of the actual CMIP data, you know, essentially what happens is like all of these different experiments are generating specific data files, right? And so these are all netcdf files to get specific, and they're characterized by a number of different facets that help you sort of find and identify the data that you're interested in. And so, you know, just walking through some of these, you know, we start from the institution, you know, which climate modeling center has produced the particular data set. We have got the source. So within each institution, they might have multiple different climate models that they run. We've got the experiment. So these are, you know, which scenario are we modeling, which emission scenario, perhaps it's a historical run, et cetera. We've got ensembles. So we haven't talked much about ensemble modeling, but these are essentially multiple different realizations of the same process. And then finally, we get down to the actual data variables within a single simulation. What's the variable name? What sort of grid does the model use, et cetera? And so this lexicon can sort of help you navigate and find, you know, climate data that's relevant to your needs. In terms of data distribution, CMIP data are distributed by an organization called ESGF, Earth System Grid Federation. So this is a federation of national labs and public sector agencies that have developed a peer-to-peer data sharing system based on netcdf files. And they also provide data catalog and search capabilities. And they've been doing this since the 90s. So it's an incredible resource for the climate modeling community. Here are some of the challenges that we see when working with CMIP data. And this could really be generalized to, you know, Earth system data in general. One, there's just a huge amount of data. So CMIP comprises over 20 petabytes of data. And in order to work with that data, you have to download it into some local storage and organize it in order to actually start computing on it and using it for analysis. And this creates a really large overhead for working with that CMIP data. There's a lot of individual sort of cleaning and organizing, you know, efforts that are made at each, you know, user of this data, which sort of hinders the reusability and reproducibility of those efforts to work with CMIP data. And so these are some of the things that are holding back the climate research community. For many years, we've been working on a much more cloud-native approach to working with CMIP data. So I started working on this at Columbia with Julius, and we continue to work on this topic at Earthmover. And the hope is that you know, we can sort of collaboratively maintain a cloud-native data repository of CMIP data that allows many different organizations, from industry to academia to government, to work directly with the CMIP data with a shared copy of the data in a way that makes their work much more reusable, much more reproducible, and much more accessible to a wider number of climate data users. So this is sort of a vision for where we'd want to go, and this is transition to the sort of final part of my talk, which is to talk a little bit about weather and climate data systems, which is really the focus of what we're doing at Earthmover today. So I'm going to give essentially a brief introduction to the platform that we're building, and then I'm going to wrap up, and hopefully we can have a little bit of time for questions. I'm looking at my watch, and I'm seeing that I'm coming close towards the end of the hour, so I'm taking my sweet time with this presentation. I think I talked a lot faster when I was doing it in person. All right, so you know, we talked about these 20 petabytes of CMIP data. I think it's worth noting that just more generally, Earth system data volumes are really exploding, right? So these are two graphs from both NOAA and NASA that show the growth in their anticipated data archives. Both of those reaching towards an exabyte by the end of the decade. So that's a 1,000 petabytes of data. So, you know, this volume of data is really challenging the sort of traditional workflows that most of us were trained on in weather and climate data science. I think the status quo is that these workflows are quite painful, right? So most data workflows today are fundamentally based on downloading files to a local server or a laptop or a workstation or something like that. So we're getting data distributed from the data providers in formats like grid, netcdf, or htf, and we're having to download all of those files. Then we have to clean and organize those files into some sort of analysis ready data set that we can actually use to do our work. And that is a very slow and time consuming process in itself, also very frustrating. Finally, we get to our analysis and modeling, which is, the fun and interesting part of scientific research. And at the end of this, we aspire to share some sort of reproducible artifact with our colleagues. And that can be quite challenging if the first step in that reproducibility pipeline is go download a petabyte of data files. That's just not something that can easily be done by a colleague. And so we see that this, traditional workflow is quite a barrier towards enhanced, speed and collaboration in the field of weather and climate data science. Our vision at Earthmover is to move towards a world where we can stop thinking about data files and simply query Earth system data as if it were a database. By database, I mean a data management system where we don't have to think explicitly about downloading data and data files and all of the sort of nitty-gritty details about how the data are stored, and we can just focus on our high-level, task and data query. Now, the challenge to achieving this is really the multidimensional nature of our Earth system data. Why can't we just stick all of this data in an existing database? Well, existing data systems are mostly defined for business data, based on the concept of tables or data frames or the relational data model, and they really don't apply to these large gridded data sets that we find throughout weather and climate data systems. And so, if you've ever tried to ingest that sort of data into a standard relational database, then you've probably seen it's a really hard process. It doesn't fit very well, and it's not a happy path to follow. So our vision at Earthmover is a cloud platform that fully understands the structure of weather and climate data. So our platform sort of comprises at the core a storage engine for efficiently storing and cataloging and querying this sort of multidimensional weather and climate data in the cloud. We have an ingestion engine that helps you bring data sets from all of these different data providers into your own data lake in the cloud. And then finally, we have a query engine that allows you to query data back out and integrate that data with all of these different applications that may have to process or work with data. And so, our platform allows you to get a high-level view of how much data your organization owns, how it's organized, how it's being used. Our platform, Array Lake, is really aimed at any number of different personas within the weather and climate data space. Companies large and small are using Array Lake as a system of record for storing business-critical weather and climate geospatial data sets. We think Array Lake has a lot of value for the public sector as a way to help organize and disseminate data in a more cloud-native and cloud and efficient way. And then finally, we really think Array Lake has a ton of value for academia as well, as a way to help a lab or department organize and manage its data holdings and share them collaboratively within those teams. So we're proud to have a bunch of great users today on this platform in the carbon data space, in the AI weather forecasting space, and also an academic lab from the University of Wisconsin. And if this seems interesting to you, we'd love to talk to you and see how we can help you with the data management challenges. Really where we're aiming to go is to help enable a planetary scale data federation in the cloud. What we've seen is that there's a lot of friction between different organizations in terms of how they are exchanging data, mostly based on the downloading and uploading of files to various file servers. And we think there's room to do a lot better. And by enabling seamless exchange of data across all of these different types of institutions, we can really empower reproducible open science and accelerate climate change solutions. So that's the end of my webinar. I've come up almost against the end of the hour, but I'd be happy to take a few questions if folks have them. Yeah, go ahead, Logan.
Yeah, just a quick question. Do you guys do anything on the hydrology side of the shop with respect to data sets that you host?
So we don't actually host data in Array Lake. We enable you to host data, right? So we certainly have customers who are working with a lot of hydrology data sets, you know, mostly around precipitation. I think streamflow is certainly one. We know National Weather Model in the US is something that is compatible with our data model for sure. But just to be clear, we're not hosting the data. We're providing a tool to help organizations of all different types host their own data and allow others to collaborate around that data.
And just to clarify, do you facilitate companies hosting data and also using that optimized data storage for their own dissemination through SaaS or something like that?
Exactly.
Okay, cool. Thank you.
Go ahead, Wasfia.
Hi, thank you so much for your talk. That was super interesting. My question is more around working in the weather and climate data science space. So like, for example, specifically working as a data refiner, as you defined it. Personally, I have like a background in climate science from Columbia, and I actually worked at Lamont for a little bit as well. And so I guess my question is, working in this space, I've gotten a lot of advice and where people are have encouraged me to get a PhD in climate science or earth and planetary sciences. So like the D's program at Columbia, for example. And my question is, like, in your opinion, to work in this space or even to work at Earthmover or all these other companies you mentioned under data refiners, would you think we need a PhD degree, or is a certificate program, or even just my background, which is a bit more interdisciplinary, but I've worked with a lot of statistics and machine learning through my work. Would that suffice?
So from a career development perspective, how do you get into this industry? That's kind of what you're asking. Yeah, that's a great question. I think what we're seeing now is what I would call an almost impossible set of requirements for folks to work at companies in the data refiner space. We see job descriptions that expect that you're going to have sort of PhD level scientific understanding and also be a coding ninja and understand how to do cloud DevOps and Python and AI. And I read these job descriptions and I'm just like, there's almost nobody that can fit them, right? And so I think part of the problem is that today the technology experience required to do large-scale weather and climate data science is very high because there's not a lot of good tooling in the space. And so if you want to do that large-scale sort of data analytics or ML, you also have to be a data engineer and a cloud engineer. This is precisely why we are building a platform that tries to make this much easier and more accessible to people. So, as a scientist, you can focus on the science and the data and not necessarily on the technology of how you actually wire together data and computing. So that's my own take on this. And so I'm hoping that this will evolve and make it more accessible for more folks to enter this field without having to get 3 PhDs. In the meantime, yes, my advice to you would be, if you want to enter this field, you need to get both domain experience with a science, whether it's through a master's or a PhD, and you need to get a lot of experience with technology. So really learn how to do, state-of-the-art AI and ML with Python, learn about all the data formats and data processing technologies. It's a lot.
Thank you. That's really helpful.
Okay, well, we've hit the end of the hour. This was a really fun opportunity for me. I'm sorry we didn't get more time for questions, but we will be sharing this out with you guys. We'll be posting it on social media, and we appreciate everyone who attended. Hopefully you learned something today. And of course, we'd also love your feedback. So we will be in touch with you. And we look forward to seeing you at some of our future events and webinars. Thanks a lot, everybody.
Thanks, Ryan.
Thank you.
Thank you.
Thanks a lot.